In this lecture, we'll look at an implementation of the bubble sort algorithm in RISC-V. One of the best ways for us to understand bubble sort is to look at bubble sort at work. So this is this is a gift animation from the web, and it's illustrating that the way bubble sort work is by making passes over the sequence that needs to be sorted, and during these passes, at each time that it visits two numbers that are nearby, it asks whether the number in the left is smaller than the number on the right. If it is, it leaves them in that order. If the number on the left is larger than the number on the right, it swaps the numbers, and it keeps repeating this process until the sequence is sorted, until it does a pass through the entire sequence and there is no need for any swaps. So this GIF animation is illustrating the process. For example, right now we're going to start a new pass. 2 is less than 4. 4 is less than 5, so no swaps. 5 is not less than 1, so there is a swap. 5 is not less than 3, so we'll have a swap. And 5 and we end at that point, and then we keep doing the swap. So bubble sort works by making repeated traversals in the whole sequence and only swapping neighboring values at any instant in time. So because of this process, bubble sort is a very inefficient sorting algorithm, but it's a simple sorting algorithm that works very well for us to illustrate how to program such an algorithm in, for example, RISC-V. So let's go back to our slides, and let's take a look at how we implement bubble sort in RISC-V. We'll start with a C version of bubble sort, and so to implement the C version of bubble sort, one of the things that I need is a swap function, because as I traverse the list of numbers, every time that I stop at two nearby numbers, I may need to swap the two numbers. So how do I swap two numbers? So in this implementation, I have a temporary, I am working with an array of integers. The array is v, and in C, this notation that says int v and the brackets indicates that the first parameter to the function swap is the address of the first element of the array v. I could have in C also have used the notation int star v to indicate that I'm receiving a pointer to an integer. And then the second parameter is the value k. Now, in the swap function in C, I will have a temporary called temp. And the way I'm going to do the swap is taking the value of the position k of the array v and put into that temporary. Then I'll take the value of the position k plus 1 and put into the position k. And then I'll take the temp and put in the position k plus 1. I'm sure that you have implemented swapping before in many of your programs. Let's look at how we're going to implement this in RISC-V assembly. The assumption that I'll make is that v, that is the address of the first position of the array v, is in the register A0, and k, which is the integer, is an integer that indicates the index into the position of the array that I want to do the swap, is in A1. By convention, in RISC-V, the first parameter of a function is in A0, the second parameter of the function is in A1, and so on. So the A registers are called the argument registers, and they are used for the argument for the function. In RISC-V, A0 is also used as the return value for a function. And then I have a temporary variable, so I'll use my T0 to store my temporary variable. So here is an example for an array that needs to be sorted. And here's my temp variable. And let's assume that I have a call to swap that swap v2. So swap v2 is telling me the initial address of v and telling me that the swap should happen at position 2. So the effect of this invocation for this function is that I'll be swapping the values 7 and 5. So when I execute this line of my C program, I'll make a copy of the value of vk. K in this example is 2. So I make a copy of 7 into my temporary variable. When I execute the next C statement, I'll be making a copy of the value that is in vk plus 1 and put it into vk. So I copy 5 into the position 2 of the array, but the value 5 remains in position 3. And now I make a copy from the temp into vk plus 1. And this is the result of swap. Let me move myself out of the way. Where is my other camera shot? And what I have now is I put these values in memory. If you do carefully examine my memory here, you'll see that the addresses in my memory are increasing by 4. Therefore, I put in a full word in each one of these boxes in my representation here in this slide. And I have the entire array here, 1, 3, 7, 5, 9, B, C, F, because this is 11, 12, and 15. 11 is B, 12 is C, and 15 is F. So this is what I would see in memory for that array. And in the processor, I have A0, and let's say that A0 contains the address of the first position of the array. So A0 contains this address here. And A1 contains the value 2 because I want to do the swap at the position 2 of the array. And T0 contains anything. I don't know what T0 contains right now because T0 has been just created. I just put a random value in T0. Now, when I execute the first statement of the swap, what will going to happen is that the value of vk, which is here in memory, so here is vk, here is vk plus 1. So the value of vk will be copied from that memory position into T0. And when I execute the next statement, what has to happen is that I need to bring the value of vk plus 1 into a register because I cannot, there is no instruction in RISC-V that will allow me to read the value of k plus 1 and write the value of vk in the same instruction. So I need to do it in two instructions. So first I need to bring the value of vk plus 1 from the memory and I need to put in a register. So I'm gonna need another register that did not appear in my C program. You can think of this as another temporary variable. And this temporary variable now I use in T2 has a copy of 5. Now I haven't finished the execution of that statement yet. I just brought the value of k plus 1 into T2. I need now to put the value into vk. So I need to take that value 5 and move back to memory to the position vk. And next, I need to take the value of temp that I have in A0, and I need to put that value into the position vk plus 1. So here, this is how the swap actually takes place between the processor and the memory. So we have the assumption that V is A0, K is A1, and temp is T0. So with that assumption now, we're going to start the process of creating the assembly code for RISC-V. And in this lecture, I'll take the opportunity to show you how I can make it easier to create the assembly code by writing what I call pseudocode first. So I'm going to start with the C statement and I'll step by step change that program to get closer and closer to what I need for a RISC-V assembly. So the first intermediate code that I will create will say that temp is actually getting the value of the memory position given by v, which is the initial the address of the first position of the array v, plus k times 4. So when I write this notation here, I'm using the notation m and the square brackets to indicate that I'm accessing a given memory position. Now you have to think that memory is an array of bytes, and each byte occupies one address in memory. So this, when I write this inside the brackets, this is actually the value of the address that I need to access. I do not need to multiply this value by anything anymore because I already multiplied k by 4. Then vk plus 1 will be the memory position given by v plus k plus 1 times 4. And I need to access that position and put that value into the memory position at the address v plus k times 4. And finally, I need to take the value temp and put in the memory position given by v plus k plus 1 times 4. So you see that this intermediate code is pretty much the same as the C address code, but I can much more clearly see the address computations that I need to do when I look at this version of the code. So now that I have this version of the code, I need to realize that I cannot load from the memory and store into the memory in a single statement in RISC-V. So I'm going to fix that by convert that single statement in my intermediate code into two statements. So for that, I need a new temporary variable. So this is my temporary variable TA. And that's all the change that I did between the two. Next, I must separate the address computation from the load, because if I'm going to do a load, I cannot have that expression for the address. Remember, the only expression that I can have for an address is a register and an offset. So I needed to separate the address computation from the access. So I'll need a new temporary variable, and when I'm generating code, I'm not using the actual name of the registers. I'm using TA, TB, TC, etc. because in my mind, I wanted to think that I have as many registers as I need for the computation. Once I have done all the process of getting closer to the RISC-V assembly, then I can decide which are the registers that I'm going to actually use for the computation. So right now, my first temporary was TA, my second temporary is TB. So I replace the expression V plus K times 4, both into the access to in the first statement and in the access in the third statement, because the expression that I compute into TB can be used for both of those memory accesses. Next, I can rewrite the expression of the address for v plus k plus 1 times 4 as TB that I already computed, that is v plus k times 4 plus 4. Because in the addressing of memory in RISC-V, I can have an offset that is different than 0 when I access the memory. And this will save me on doing additional address computation that would not be necessary. So I have now replaced that access with TB plus 4. Notice that by slowly changing the intermediate code one step at a time, I'm ensuring that I'm making everything correct, and each step is easy to do. Of course, if you're doing this on paper, you end up writing a lot, but you could simply make a copy into a file of your original C program and start doing these modifications in place, or simply making copies of that content of the file so that you can follow your steps. Now I have this expression v plus k times 4 involves both a multiplication and an addition, and I cannot multiply and add in the same instruction in RISC-V, so I need to separate that into two statements. So what I'm going to do now is I'm going to write the value of k plus times 4 into TB, and then add the value of v to it, or added that to the value of v, to get a new value for TB. I don't need to get yet another different temporary variable, although I could, because this is a very local computation and I can reuse the same temporary TB. So what I have now, I have k times 4, v, and temp. And in my assumption, this must be these registers. So I can now replace them. So this was v, that was the first argument to the function. This is always a 0. And k is the second argument to the function. It's always a 1. So I'll replace those by the registers. And I will also replace the k times 4 with a shift left by 2, because I know that when I shift a binary value to the left by 2, this is the same as multiplying by 4. So now I have to choose a register for TB, and I chose to use T1 for TB. So everywhere where I had TB, now I have T1. As you can see, we are getting very close to a RISC-V assembly now. So now that I have this intermediate code, it should be fairly trivial for me to write my assembly code for the swap function. Shifting left by 2 is the shift left logical immediate instruction, and then I have the add instruction. And notice that here on the right hand side, I keep in comments what my instructions are doing, because that will be much easier for me to understand my program when I come to revisit it later. So next I have 2 memory accesses. Which instructions do I use to make memory accesses? In this case, the vector is a vector of integers, so I'm going to use the LW instruction that will bring a word from memory. So I'm going to need 2 load word instructions. The first one will have an offset of 0, because the address of the memory that I needed to access is already in T1. But the second load instruction will have an offset of 4, because I need to access the address T1 plus 4. So here are my 2 load instructions that are bringing those 2 values from memory. And next, I have 2 store instructions to memory, and it's the same thing. The first store instruction will have an offset of 0, and the second store instruction an offset of 4. And this is what I need to do for the code of my swap. All I need to do now is to return. Swap is a void function, so there's nothing to return, so I do not need to do any instructions to write anything into a 0 in order to implement swap. So here I have my return statement. In RISC-V, the return statement is the jump and link relative instruction, JAR, and I always use 0 as the register. I use array, and I use a constant 0 as the offset for the instruction. So this was the explanation for the swap procedure for my bubble sorting implementation. In the second part of this lecture, we'll look into how we implement the sorting procedure, which will be calling the swap procedure to do the swaps when a swap is necessary.